All right. Hey, so we're looking at some frames of reference and relative velocity questions. So these are questions that are dealing with the concept of the fact that if you're moving through something that is already moving, then your velocity could be considered different depending on what frame of reference you're sitting in or the viewer is located in. Okay, so for example, if I'm, take this canoer for example. This Olympic canoer is traveling at a speed of 4.5 in still water, right? So if you're in the water, you could see if you're sort of sitting in the water, sort of hovering or whatever. What do you call that? Paddling, treading. That's what it's called, treading the water. You would see the canoeist going by at 4.5 meters per second. If you're in the canoe with the canoeist, you would see the canoer with a velocity of 0 with respect to you. And then if you're on the shore watching the canoer going at 4.5, but then the water is flowing, then you would see the canoeist at a completely different velocity on top of that. So that's this idea of a frame of reference. It depends on what reference frame you're looking at that you would use to calculate the final velocity or the actual velocity of the apparent velocity of the canoeist, right? So with this sort of concept in mind, we end up in physics, classic physics questions deal with situations like this. And so one of the most typical ones is, this water in a boat crossing a river type thing, right? So we got an Olympic canoeist capable of traveling at 4.5. It's crossing a river, and the river is flowing at 3.2, and it's east, 3.2 east, and we have a 220 meter wide river. If the canoe is aimed northward, what is the velocity relative to the shore? So I'll go ahead and take a look at this part A here. I'm going to go ahead and draw a situation here. So my canoeist is pointed northward at 4.5 meters. Then there's the river that's moving at 3.2 as well. And that's happening to be going at east. And if you combine those two velocities, then you would actually see the canoeist move in sort of this direction. Here's my canoe, and maybe I can grab it. Here it is. So the canoeist is going here, but the water is pushing it that way. And so the combined motion of the canoeist in the water would be a situation where it moves like this, okay? And so that's something we want to keep in mind, okay? The question is what's the velocity relative to the shore? Well, this is the velocity relative to the shore. And now, noting that these are at a right angle, the velocity relative to the shore is simply 3.2 squared plus 4.5 squared, and that's rooted because this is just a simple Pythagorean theorem. So we're going to get a 5.5 meters per second, okay? How long does the crossing take? How long does the crossing take? Well, for part B, what we, hang on a second. Before I move on, actually, this is just the speed of the canoeist. I want the velocity. Remembering that velocity is a vector, and I have to put the angle on there. So trying to figure out this angle, I'm going to use tan inverse of the opposite side, which is 3.2, over the adjacent side, which is 4.5. And I end up getting about, I think, 35 degrees. And so the velocity of the canoe is essentially at 5.5 meters per second, and it's 35 degrees from north towards the east. So you could write that as 5.5 meters per second at 35 degrees east of north. Okay. Now the question is, how long does the crossing take? All right. How long does it take to cross the river? There's a couple of ways of doing this. I find the most appropriate way is, let's draw our river here and here. And now let's remember that the canoeist is moving at 4.5 directly north. Okay. It's true that the river is pushing the canoeist over, but all of this river velocity is wasted in that it doesn't do anything towards allowing the canoeist to travel across the river. And the only useful velocity is this 4.5. So I don't want to use this 5.5. I don't want to use the 3.2. I actually just want to use the 4.5 because that 4.5 is isolated it is doing one thing, and it's allowing me to cross this river. So what I can do is I can kind of just say, look, my velocity in the north direction is equal to my displacement in the north direction divided by my time. Okay. And so my displacement in the north direction should be 220 because that's how long it takes, or that's how far I should go. My velocity in the north direction is 4.5. Using this formula, I should be able to find the time. And a little bit of algebra is going to tell me that the time is equal to the displacement divided by the velocity. So 220 meters divided by the velocity of 4.5 meters per second. And I'm going to get a time here. Okay. And so it looks to be like it's going to be about 49 seconds. All right. Where is the landing position of the canoe relative to its starting position? Relative to its starting position. So let's look at this one, part C now. Let me move this guy down a bit. All right. So here, this one is talking about the actual physical makeup of the river. So here's my river. Here's my thing. I do know that the canoeist is moving such that it's a 35-degree angle here. And if he ends up just continuing that the entire way, that angle is pretty bad. It looks a bit exaggerated. I wanted to erase this here. I do know that the canoeist is moving at a 35-degree angle, and they're just kind of moving and moving and moving, and boom, they're going to land right here. They're starting right there. So the question is relative to the starting position, how far down the river do I end up landing here? All right. Well, this is just another right triangle where this is a meter, right? 220 meters. This is 35 degrees. And over here is the kind of distance that I'm looking for, right? Noting that this is going to use my SOHCAHTOA. This is tangent. I'm going to use tangent. So I'm going to say that the tangent of 35 degrees is equal to the opposite side, which is the value that I'm looking for. I'll leave a question mark, divided by 220 meters. Okay. And if we end up doing that, let's see, it's about 160, I think, is what we're going to end up getting if we solve for this. So it's 220 times the tangent of 35 is this question mark distance. Okay. I didn't want to do that. So it's 200, sorry, no, not 220. It's 160 meters. So apparently this is about 160 meters downstream. So Maybe we could say something like that, 160 meters downstream. Okay. Well, let's go see what else they're asking us. If the canoe landed directly across from the starting position, at what angle would the canoe have been aimed? Oh, this is a completely different situation. Okay, so what's going on here is they're going to try. So the canoeist is going to be attempting to. So let's draw our river again. Boom. This is part D. And they're going to start here. And they know that they're able to swim at paddle at some kind of velocity down into this direction. And then, which is 4.5. But they also know that their velocity of the river is 3.2. And they're going to want to make it so that the combined velocity of their velocity and the river velocity makes our canoe. So here, let me make my canoe again. Makes my canoe. So I'm going to point my canoe in this direction and try and swim in this direction. But because of the velocity of the river, it's pushing me back. I'm going to attempt the effective motion of my canoe is going to be straight across. And if I am able to do this for the entire time, I could effectively land my canoe over here. All right. So basically what's going to end up happening is what I just said there. So I need some sort of velocity such that it's 4.5 and 3.2 such that they result in a velocity that's pointed directly across the river. And I only need to know the angle because the question asked, what's the angle at which they need to point the canoe? And again, so this is just a simple, I have my opposite side here and my adjacent side. Sorry, no, I have my opposite side and my hypotenuse. So I'm going to use the sine function. So the sine of theta is going to be the opposite side, or 3.2 over 4.5. And now if I solve for this, I'm going to do sine inverse of 3.2 over 4.5. Okay, and that's going to be the angle that I need in order to paddle at my maximum speed, and accounting for the river flow, also end up landing across to the other side. And apparently, after you do some algebra or whatnot, some typing into the calculator, you end up with a 45-degree angle. Is going to end up achieving that value. Okay, so there's our canoeist question. Some pretty interesting stuff. Other typical questions that involve. I don't know. I've got this placed twice here. I only want one of these. Is a situation where you've got airspeed. Okay, so you've got an airspeed of an airplane is 215 kilometers per hour. The wind is blowing at 57. Determine the velocity of the plane relative to the ground if the pilot keeps the plane aimed in the direction 34 east of north. Okay, so kind of drawing this out, here's my sort of two vectors. I've got the pilot is pointed at 34 degrees east of north. So it's like this, somewhere up in here, 34 degrees. And he's able to travel at 215 kilometers per hour. Okay, that's a 3. I meant a 2. 215 kilometers per hour. But then I also have a wind that's blowing directly from the west. So it's going to push me in this direction, which is a total of 57 kilometers per hour. So therefore, my resultant actual velocity relative to the ground is going to be this. Because if I'm pointing sort of northeast, and then I've got a westward wind pushing me, that means I'm going to be going a little bit more northeast, a little bit more towards the east than I would have normally been going. Okay, I guess is what I was trying to say. All right. And so now, essentially, what we're going to want to do here is just add these two pink vectors to get this fuchsia vector, I guess is the name of that color. And so we'll do that. Okay. Now, because I tend to use the component method for this. So I'll show you what I tend to do. So the velocity of the airplane plus the velocity of the wind tends to give you the ground speed. Okay. This is a formula that you can kind of use. Well, the airspeed velocity is 215. So I'm going to use the 215 sine of, now I have to figure out what is this angle in trig bearing, because I'm going to use my calculator. Okay, right? I'm going to use my calculator, and so because I'm going to use my calculator for this, what is this? This angle. So this is 90. If I take off 30, that's 60. Take off another 4, that's 56. So the sine of 56 plus this this eastward velocity, which has an angle of 0. Okay, so plus the wind speed, which is at 57 sine of 0. Then I have to do 215 cosine of 56 plus 57 cosine of 0. And with these two, I'm going to get my y component of this pink vector and my x component of the pink vector, or the fuchsia vector here. Okay, so when I end up typing all of this into my calculator, I end up getting, what do I end up getting here? Let me, so yeah, there we go. So that was it. So it's 178 in the y direction, type that into the calculator, and 177 in the x direction. So effectively, this pink vector has a 177 vector here and a 178 vector here. It looks like it's going to be going at 45 degrees about. Okay. So the actual velocity itself is the square root of 178 squared plus 177 squared. Okay. And we end up discovering that that value is 251. 251. That's kilometers per hour. And then the direction here is going to be, again, a tan inverse of the y component, 178, over the x component, 177. And I'm going to effectively get a 45-degree angle there. Okay, so my velocity relative to the ground is equal to 251 kilometers per hour. And it's at east. Sorry, I'll write it in, I could write it in any kind of, so it's like 45 degrees north of east. Okay. So there's a couple of relative velocity style questions for you to practice up on. Okay. Let's see here.